Alright guys, this is illustration and code implementation for Dijkstra's shortest path algorithm. So first of all, you need to be familiar with the graph theory. So what you need to know that we could convert any graph, whether it was undirected or a directed graph, into an adjacency matrix. So this would be the adjacency matrix to the graph. And the way we read this is by going from a row to a column. So I would say vertex 0 is connected to vertex 1 with an edge of entropy 4, right? 0 is also connected to 2, 3, all right? So this would look something like this. So 0 is connected to 1 by an edge of entropy 4, all right? And I can't look at it the other way. So I'm not able to say 1 is connected to 0. It's not. 0 is connected to 1 only. And in the code, I'm going to fill the blank spaces with -1. So here -1, -1, and the diagonal line with zeros because it would take us 0 time to travel from 0 to 0 and 1 to 1 because we're not moving. All right. So just keep that in mind. And I'm going to start the algorithm. So the first step is we need to give properties to each vertex. So we have three properties, which are the cost of time, all right, and the path, and also the state. So the state is either visited, I'm gonna mark visited by a red circle, and unvisited, all right? So the path is the previous vertex. So let's say I went from 0 to 3. So the path to to vertex 3 would be 0 because I've came from node 0, all right? And the cost is basically, so if I went from 0 to 3, the cost of 3 would be 7 because it has taken me 7, all right? So initially, the first step is I want to initialize all the vertices to a cost of infinity and a path of null or -1, right? So -1 or null, right? And the state of all the vertices are going to be unvisited yet, all right? So just keep that in mind. And the first step is we need to decide the start node. Which one is the start node, all right? So in my case, the start node is going to be 0, all right? So I'm going to mark this as visited. And before that, let me mark the initial values to each vertex. So this is the path, -1. It means we didn't come from any vertex before 0. This is the start one, right? And the cost is infinity. So I'm gonna mark, okay, so now I've marked all of them, -1 as the path and infinity as the cost. So the first step is you're gonna decide the start node and mark it as visited. And then we're going to change the cost from infinity to 0 because it would take us 0 time to go from 0 and back to 0, from the start node and back to the start node. All right. So the next step is we're going to look at the adjacent vertices, which are 3, 1, and 2, because we have an edge, connecting them. So one condition should hold in order for us to relabel the unvisited vertex, which is if the cost of the visited vertex, which is 0, plus the entropy of the edge, which is here 7, 4, and 2, is less than the cost of the unvisited vertex. If this condition holds, then we're gonna relabel the vertex. If it doesn't, we're not gonna do anything, right? We're gonna keep it as it is, right? So let's try vertex 3. So what I've said, the unvisited vertex cost, which is infinity, should be greater than the entropy 7 plus 0. Is this true? Yes, it is. So if it's true, we're gonna relabel this. Uh, Here it's gonna be, so the path is gonna be 0, and the cost is gonna be the entropy of the edge plus the cost of the previous vertex. So it's gonna be 7, because 7 plus 0 is 7. All right, and we're gonna do the same thing for 1 and 2, right? So is 0 plus 4 less than infinity? Yes, it is. So we're gonna relabel this and this also because it's infinity. So this is gonna be 0 and 4. This is gonna be 0 and 2. So step 2 is we need to check among all the unvisited vertices which one has the least cost. So these four they have infinity cost. So we're looking at these three. The minimum one with the minimum cost is 2, which is not 2, right? So what we're gonna do is we're gonna mark this as visited with a red circle. And we're gonna do the same step that we did before, right? We're gonna look at the adjacent vertices. So in this case, it's gonna be 5 and 6, right? So we're gonna check for the right? So is infinity greater than 2 plus 9? Is the cost of the visited vertex plus the entropy of the edge. So this is true. So I'm gonna do is relabel this. I'm gonna the path is gonna be 2 because I came from 2, and the cost is gonna be 11, right? And same thing here. The path is gonna be 2, and the cost is gonna be 5 plus 2, which is 7, right? So now we're gonna check again which one among all unvisited vertices have the least cost. So in this case, it's going to be, so we're not looking at the visited ones, right? 0 and 2. We're only looking at the unvisited ones. It's going to be 1, node 1 with cost 4, right? So I'm going to mark this as visited. So here we only look for the adjacent vertices that are not visited. So I'm not going to change 2. If a vertex is visited, it's not going to change, all right? Um, so we only have 3 here, all right? So I'm going to check for the statement. So is 7, which is the cost of the unvisited vertex, greater than the entropy 8 plus the cost of the visited vertex, which is 4. So this is 12. This is 7. All right. So this is not true. All right. So we're not gonna change the vertex properties because this is 7 is a shorter path than 12. So we're not gonna change it. Okay. So now we're gonna check again which vertex unvisited vertex has the least cost here. So 7 and 7, here we have 11. So it's 3 or 5. We could pick any one. I'm gonna pick 3. So 3 is connected to 5. I'm gonna check for the statement again. So is 7 greater than 7 plus 9? It's not. So we're not gonna change anything here. And the same, now we're gonna check for the least one, which is 5. 5 is connected to 1. So we're gonna check is uh, is 4 greater than 7 plus 5? No, it's not. So I'm not going to change anything here. Uh, Also, it's only connected to 1. All right. So now we're going to do the same step. Is this 2? Yeah, it is. All right. The same step. So we're going to pick 6. We're going to check for the condition here. Is infinity greater than 11 plus 8. Yes, it is. So we're gonna relabel this. It's gonna be 6 and 11 plus 8, which gives us 19. Right? Now I'm gonna check if it has any more. Alright, so it's connected also to 5, but 5 is already visited. I'm not gonna change that. So now we're gonna pick the down visit vertex with the minimum cost, which is gonna be 4. I'm gonna mark it as visited. It's not connected to any unvisited vertices. So in this case, I'm gonna check for the least one. The least one is gonna be this one, right? So I can't visit this. I won't mark it as visit because there's no connection. We can't go from the start node to node 7. So it's gonna stay as infinity in this case, all right? So now the algorithm is finished. We stop the algorithm when all the vertices are visited, or when all unvisited vertices have a cost of infinity. Just in our case, because 7 was unvisited, but it has an infinite cost. So in this case, we're gonna stop the algorithm. And the way we get the path is by reversing back. So let's say I want to go from the start node 0 to 6, for example, okay? So let's say 6 had uh, path 2 and cost 11. So I know that the shortest path to 6 is going to cost me 11. And how do I get the path? I just write, okay, from 6 to 6, 2, because the path is 2. So this is going to have a cost of 2 and path 0. So I came from 0. So 0 to 2 to 6. So the verses have all the informations we need in order to get the path and the minimum time. All right. So now we're gonna see how would this work in a C program. Okay, now the coding part. So just gonna include standard output library, and most importantly, I'm gonna include the math.h, which has the infinity variable because we're gonna use that. As I said. So also I'm going to define some variables. So I'm going to define the size of my matrix. It's going to be 10 by 10. And I'm going to define visited as 1. I'm defining unvisited as 2. All right. Now I'm going to define the matrix. So 10 by 10 matrix, I'm going to initialize it to 0 just to be safe. I'm going to use an enumeration just to identify the cities as letters. So it's going to be from A, B, C, D, E, F, G, H, I, J. So this is going to give the value of 0 to A, all the way 1, 2, 3, all the way to J9. All right. So I'm going to make a struct that holds the properties of a vertex, right? I'm going to name it vertex. This is going to have 4 properties. First of all, the character of the city, and the cost, also the path, yeah, and the state, which is either visited or unvisited, right? And it's an integer because I've defined it as an integer here. Now I want to make an array of the vertices. I'm gonna name it vertices, right? We have 10 of them. Now I want to initialize write the prototype of the function. I hope I've written this correctly. I don't know. So this is gonna take the source as an integer, also the destination as an integer. All right. Also, we make a function that scans the matrix array, adjacency matrix. So yeah, I'm gonna name this adjacency matrix because that's what it is, adjacency matrix. All right. So now defining the main function inside here, gonna wait, then return 0, just basic stuff. I'm not gonna explain C programming to you. So first I'm gonna scan the array. Gonna call, gosh, let's say I want to go from A to D, right? Then what do I need to do now? Right, let me copy this and side here, can define an integer, nested loop, size, size, right? I'm gonna scan for an integer and I'm gonna save it in C, right? And then I'm gonna call that into matrix I j is gonna be equal to C. Alright, so now I just have to define the Dijkstra's function right here. So first of all, we're gonna initialize the properties of all the vertices. So how we're gonna do that? I'm gonna make a for loop, and then inside here I wanna call this vertex, right? Into the size. So here vertices, vertex dot city. This is gonna be equal to vertex plus 65. So this is gonna convert. So if it's 0, it's gonna be A because I've added 65 because in ASCII A is 65 and B is gonna be 66 all the way to J. So I'm gonna call this again vertex dot initializing the cost. As I said, it's gonna be infinity at first and the same here for the path. It's going to be null or -1. I'm going to stick with -1. Um, by the way, minus null is -1 basically, so it doesn't matter what. The state is going to be unvisited. Yeah, did I know it unvisited? Okay. Now what I need to do is I initialize the cost of the source or the start node as 0. This is gonna be equal to 0. I'm gonna make an endless loop. Alright, so I'm gonna do this. And it's gonna end when if the current, I'm gonna explain what is the current in a bit, is equal to -1. So if this is the case, great. So uh, so this is gonna break when all the vertices have been visited or all the unvisited vertices have infinity cost. Alright. So how are we gonna do that? Uh, uh, but before that, I need to find the vertex with the minimum cost upon all unvisited vertices. All right. So I'm gonna this is a variable holding the minimum cost. I'm gonna initialize it to infinity in case there was no minimum. So it's gonna be equal to -1 initially. I'm gonna make a for loop that iterates over all the vertices. So vertex size. So if the vertex cost is less than the minimum cost, then this is a new minimum cost basically. And I want it to be unvisited, right? So I'm only checking the unvisited ones, right? So vertices vertex dot state should equal unvisited, right? This makes sense. Now, if this is true, I'm gonna change the minimum cost to the new minimum cost, which is vertex. Also, I want to change the current vertex because when we find the minimum one upon all the unvisited one, we're gonna make it the current one, and I'm gonna go from there and run the algorithm again. All right. So if this is never satisfied, so this is never satisfied when there's no vertex that is unvisited, or when uh, there is no minimum cost. So all of them are infinity. All right. So if this is the case, this is not gonna change the current, which is gonna break the loop. So now we're gonna check for the condition whether the cost of the visited vertex plus the entropy of the edge is less than the cost of the unvisited vertex. So I'm gonna do that, but before that I need to uh, mark the current uh, vertex as visited, right? And now I'm gonna make a for loop, uh, vertex size. So we need to check the adjacency matrix now if there is even a path from our vertex to the next one. So we need so let's say the current vertex is 0. How do I check the connections from 0? I go to the row that is 0 and check if we have a 0, then this is an edge to itself. So I don't want that. And if it's a -1, it means there's no edge. So I want to check for that. Basically, I want to write not equal to 0, right? And and I want the vertex to be an unvisited vertex. So state is going to be equal unvisited. And I don't want to equal -1 because that means that there is no edge connecting the nodes. So -1. Now I want to check for the other condition, which is if the wait, the vertex, the visited vertex cost, which is gonna be the current one, all right? Cost plus the entropy of the edge, which is I'm gonna refer to the adjacency matrix for that. It's gonna be the current and the vertex. If this is less than the cost of the unvisited vertex, which is like this, the cost. If this is true, I'm gonna relabel the vertex. So I'm gonna do that. Vertices, vertex dot cost is gonna equal this, right? And the path is gonna change also. So vertex dot path is gonna equal the current because I came from the current vertex in order to reach the next one. All right. So now we're done with the algorithm. This loop is gonna keep relabeling the vertices until it can't anymore. Okay, now the algorithm is almost done. So now I want to find the path. So the parameters of the function it takes a source node and a destination node. So I want to find the path from the source to the destination node. So first of all, I want to check if the destination node is even reachable from the start node. So destination dot cost not equal to no. If it's equal to infinity, then I'm gonna display a message. This printf the two cities are not connected. New line. Right. Else, we could like make a string that holds all the city values, like the node 0, 1, and then when we are gonna read it, we're gonna read it the other way. So from the end to the start, it's gonna give a it's gonna give us the path. So I need define more variables. So let's call this path. All right. So 50. Initially the cost is gonna be 0. I want to calculate the cost as well, and the count is gonna be 0. This is gonna help us know how many characters we've added to the string. So when we loop over it, I know when to stop. So as long as the destination is not the source, so we have not reached the source yet, because I'm gonna give the destination a new value each time I iterate in this while loop. So I'm gonna increment the count by 1 each time, and the path count, I'm gonna add the destination, which is the current path. So I'm gonna put x equal to the path of the current vertex. So if you want to go from 0 to 6, I'm gonna go to 6 first. I'm gonna add the 6 to the string, and then I want to add the path. All right, I want to add the cost as well. So cost is gonna be equal like this adjacency matrix x and destination. All right, I hope this makes sense. And the new destination is gonna be x. We're gonna keep doing that until we're done, until we reach the start node. All right. Now we need to add the source node because this is not gonna add it, okay? Because it doesn't satisfy this. So when the destination is equal to the source, it's gonna uh, end the loop, and now I just have to add the source to the string. And now I need to write a for loop that goes through the string from the end to the start, right? This is gonna look something like this. So I'm gonna decrement this, and as long as this is greater or equal to 1, this is gonna equal count. Right, so now I'm gonna print. You could return this from the function. I'm just gonna print it right away. So vertices, right? Uh, path I. So this is gonna give us the uh, the vertices as numbers, right? I want to convert this to the letters A, B, C through J. So I'm gonna do that. I'm gonna put this as the index and refer to the city. This is gonna give us the letter. So between each letter, I wanna put like a dash, unless it's the last one. So I'm gonna do that if I is greater than 1. Printf So if it's equal to 1, it's not gonna print the dash. Now I want to print it the cost. So percentage D line. This is gonna be cost. So now we're done. I just need to run this. So now we're just gonna run the code and hope for the best. So the input file is gonna be this, right? So this is an adjacency matrix, and here I want to go from A to D. So I'm gonna input this to the code, and as you can see, a diagonal line has zeros because it's connecting to itself, and -1 as there is no path connecting the nodes, right? So here I have A, B. So B has no edge connected to A, which is here, all right? I hope that makes sense. So I'm gonna uh, run this. So now it gave me the shortest path, which is A to C to D, which is gonna cost me 20. So this has been the video so far. I hope I did a good job explaining this to you. Uh, this is my first video, and I was really nervous. So I'm gonna keep uploading like data structures, algorithms, maybe programming database, uh, Java, whatever, whatever courses are in computer science. Because I've not seen many resources on YouTube. They just make it look intimidating, you know, they they complicate the concept, right? And I want to make it simple for you guys, as simple as possible. So I hope I did a good job doing that. And if you're interested in these topics, you could subscribe, and I'm gonna see you in the next video.